third episode of the series. This time we're diving into algebraic equations and differential equations, two fundamental tools in mathematics. Now we look at their differences, similarities, and their applications. Also, we will see how they appear in sciences.
Now, as you know very well, algebraic equations, the most covered concept in high school mathematics, involve numbers, variables, and algebraic operations, such as the fundamental four: addition, subtraction, multiplication, and division. And often techniques like factoring, substitution, or standard formulas like the quadratic formulas. We also have powers and logarithms, and essentially they are numerical in nature, and a set of equations uh, with the same number of unknowns can always be solved to give various values. And this forms the basis for quantitative physics and chemistry.
And you may ask, where are they used? A classic example is in chemistry, where algebraic equations help determine the equilibrium concentrations by balancing reaction equations.
Or the entirety of stoichiometry, kinematics, nuclear physics, and even astronomy. Wherever you see it, wherever even the simplest numerical model is used, we will see that algebraic equations come into it. Now, on to differential equations. These involve the derivatives of functions and the functions being expressed in terms of their derivative. They express rates of change and how one variable depends on the other. When a differential equation involves a function of more than one variable, it involves partial differentiation, and they're known as partial differential equations. But for contest level and high school level, you would typically not need more than single variable differential equations, but they have properties like degree and order, which we will come to and explain more in the transcript. To solve differential equations, you must have come across techniques in 11th grade or 12th grade calculus, like variable separation, homogeneous equations, or the integrating factor method.
But what happens if solving the differential equation directly isn't feasible? That's when numerical techniques like Euler's method are used to approximate solution at specific points. Now, Euler's method is an algorithm that is used to approximate a differential equation value.
So now on to how do algebraic and differential equations actually differ. In algebraic equations, of course, we solve for specific values of variables, while in differential equations, our solution would be a function that describe how variables change over time or space or another variable.
Now, a key concept in differential equations is the initial conditions. These specify the value of a variable like y at a given x. Why are they so important? Because differential equations often give solution to an infinitely many functions. However, the initial conditions helps pinpoint an exact function and solution.
Well, that brings us to their purposes. Algebraic equations are used, like I said earlier, to find unknown values or relationships between numerical variables. When dealing with multiple variables, multiple equations are needed. Some systems of equations, whether linear, quadratic, or any degree, some systems have many solutions, which are infinitely many solutions. Some have a single solution, some have no solution. To obtain the maximum number of solutions, you need to have as many equations as you have unknowns.
On the other hand, differential equations define systems, describing how quantities evolve or interact. For example, simple harmonic motion is a great example of differential equations in action. Now, SHM is a topic in physics, and the motion of a mass on a spring is following a simple harmonic motion. For example, a simple harmonic motion equation looks like d square x by dt square plus k by m x, which is equal to 0. Here, calculus helps describe oscillations, with solutions like x of t is equal to a cos omega t, predicting the position over time.
And again, without calculus, it would be essentially impossible to know what the period of a spring lock oscillator or a pendulum looks like. Another example to add on is Newton's law of cooling, which says that the rate of change of temperature of a body is proportional to its temperature difference with its surroundings, Ts. So as a result, calculus is very important in physics, and as you'll see later, it also comes into chemical kinetics, thermochemistry, and so on. But their parallels are very similar in both physics and chemistry. Before we wrap up, let's try a challenge. Try solving the equation dy by dx equals 2y over x times ln y. This will be, the solution is provided in the transcript, but here's a hint. This is a variable separable equation, so you can start by integrating both sides, and don't forget to use the initial condition.
And that's all for today's episode. Check the transcript for detailed examples and solutions. In our next episode, we'll uncover the mysteries of probability.
Cut, say that again.
Okay. And that's all for today's episode. Thank you very much. In our next episode, we'll check high school concept tricks. Thank you.
Thank you.